So take a look at this function. The graph of the square root of x. It's an old friend. You've probably seen this scores of times at this point. And what I want to focus on is what's going on at x equals 0, right there on the far left-hand side. The function is pretty well behaved at that point. It's defined there, right? The function, it doesn't have any weird gaps. It doesn't have any breaks or twists or there's nothing strange going on. It's even defined at 0, right? F of 0 equals the square root of 0, which is just 0. But here's the problem. What is the limit of f of x as x approaches 0? Here we run into some trouble, right? Because if you pick any open interval around y equals 0, right? There's your epsilon. I cannot pick an open interval around x equals 0 where every number in that interval gets mapped into yours. No matter what interval I pick here, right? If I pick it small enough, I'm going to be okay on the right-hand side. On the left-hand side, I'm just doomed. The function doesn't exist over there on the left side of 0. So because the x values on the left side of 0, for whatever reason, see, the reason doesn't matter here. The x values on the left side of 0 are not getting mapped into that y interval. Therefore, this limit does not exist. And that's a little bit of a problem for me because I want to be able to talk about that point. I want to be able to talk about limits at that point as if it was a normal point, because the function is fairly well behaved there. And here's how we're going to do this, right? We're going to kind of drill down a little deeper into this concept of a limit. And what we're going to do is we're going to define the limit of a function on each side of a point, right? So you notice if you look carefully here, there's a little plus sign here and a little minus sign here. Okay, the minus sign means this is the left-hand limit, and the plus sign means this is the right-hand limit. And these kind of mean what you think you're going to mean, right? To evaluate the right-hand limit of a function at a point, you're only going to look at the values on the right-hand side of that point. So to come up with this limit here, as x approaches 0 from the right, I'm going to completely ignore negative numbers. Completely ignore the numbers over here on the left side and only look over here on the right. And from the right-hand side, the function is doing good things, right? It's defined over there, and the function, as we get close, as the x values get closer to 0, the y values get closer to 0, and that is what this limit equals. Right, now over here on the right-hand side, when we want to talk about the limit from the left, okay, well here we're still in trouble, and ultimately there's no getting around the fact that the function isn't defined on that side, right? So while the limit as x approaches 0 from the right exists, the limit as x approaches 0 from the left does not exist. Okay, so that's again, that I'm kind of following the same approach as I did when we first talked about the two-sided limits, which is kind of our regular limit now. That's just a very kind of heuristic approach, right? It's just looking at the picture and saying, okay, this is what we're talking about. There is a formal definition, and we'll get to that in a minute, but I want to keep looking at these things in kind of a practical sense so you can see what we're talking about visually. This function here kind of illustrates all of the different situations that can come up. So I'm going to look at a bunch of limits here. First, what is the limit as x approaches 0 from the right? Well, go over kind of the right-hand side of 0 and look at what the function is doing. On this side, it's dropping. Whoa, that became a mess. On this side, it's coming down here, and the y values are approaching 1. Okay, well, how about from the left-hand side? I'm going to do the same thing. Look at the left-hand side of 0. That's over here. And on that side, the function is approaching -1. All right, so let's try another one. How about the limit as x approaches -2 from the right? Okay, -2, that's over here. And I'm going to kind of go to the right-hand side and look at what the graph is doing. From the right-hand side, it's also approaching -1. But if we try to do the same thing, oh, there's supposed to be a little minus sign in there. I got left out. That should be 2 from the left. Over here on the left-hand side of 2, the function is undefined. Okay, so over here, the limit does not exist. All right, so let's try one more. Let's see what's happening at that gap over there at 1. As x approaches 1 from the right, so I'm going to go to x equals 1, go a little bit to the right, and what's the function doing? Well, it's coming down on this point right here, and the y-coordinate of that point is 2. How about we do it from, that's 1, good. How about 1 from the left? Well, that's coming in from the other direction. I'm still coming in on that same point, and the y-coordinate of that point is 2. Okay, so now I want you to stop for a minute. Right? I want you to stop for a minute and think about the overall limits. Think about the two-sided limits. What is the limit as x approaches 0 of f of x? Well, it doesn't exist, right? Because we're coming into different points. Over here, it's coming into this point, and up here, it's coming into a completely different point. This limit does not, I'm going to abbreviate, does not exist. Okay, so how about as x approaches -2? Well, now we have the same problem as we have with our square root function. It's defined and behaving well over here on this side. Over here on this side, it isn't defined. So this limit, the limit as x approaches -2, also does not exist. All right, so finally, how about the last one? How about the limit of f of x as x approaches 1? Okay, well, we've seen this situation. Right? We've seen a situation where we have a function, and there's just a hole in it. Right? And when we saw all of these before, this limit is equal to 2. And I want you to notice something here. Notice that all 3 of these limits are the same. All right, we're going to come back to that in just a minute. Right? Hold that idea in the back of your head. All right, so here's our formal definition. And if you're taking notes, whatever you want to write this down, you can pause this for a minute. But before you do, I want to make a point about this. All right? This whole definition is practically a carbon copy of our previous definition, of our two-sided limit definition. The only difference, right, there's 2 differences. First, it starts off with this part. Now our function only has to be defined to the right of c. I don't care about what's happening to the left anymore. And this is a difference. Right? You remember our previous definition was the absolute value of x minus delta, the absolute value of x minus c is less than delta. And when we went to solve this absolute value inequality, it became negative delta less than x minus c less than delta. Then you can add c to both sides. C minus delta less than x less than c plus delta. Okay, so in other words, this definition is saying take our point C and go up delta and down delta, and that's the interval that we care about, the open interval. This one is saying, no, look. Instead of going down to here, we're going to stop at C. So what's that going to look like? Well, instead of being here, it's going to start at C and go up C plus delta. So that's the only difference. Right? The only fundamental difference is that this inequality is changed and it's just rephrased in a way that is saying just look at the right-hand side of C. Right? Everything on the right-hand side of C has to map into that interval around L, around the limit. And down here, that's for a right-hand limit. And down here, for a left-hand limit, we're going to do the same thing. Now we're going to say we're looking only at the open interval between C and C minus delta. Those are the numbers to the left of C. Those are the only ones we're going to require for the left-hand limit. Okay. So, math people, anytime we define a new thing that's kind of similar to an old thing, right, kind of the first question we ask is, well, is there a connection between these two? Is there a connection between these left and right limits and two-sided limits? So I have a theorem here, and it's going to give us this connection explicitly. But I want you to read through it. But these calculus limits, they all tend to follow a similar pattern. They always have to spend a sentence or two setting everything up, and then they'll finally get to the point. And that's what's going on here. They're saying, look, first, suppose we have a function, and it's defined on an open interval around some number c, right? That's going to be the number we're taking the limit at. And it doesn't have to be defined actually at that number. Okay, if this is true, then, and sorry, I got to make a little correction here. These should be c's, not zeros. Then, and this is the meat of the theorem, the two-sided limit, that's this side, exists if and only if the left and right-hand limits exist and all three of them equal the same number. That's exactly what we saw with two sides back, right? We had the limit as x approaches 1, I think it was, and I made that point. Look at this. All three limits came out to the same number. That's what this theorem is saying is going to happen. Okay, so let's see how we can prove this real quick. If you're not into the whole proven thing, you're welcome to skip ahead to the next slide. But this one is actually pretty straightforward. Now remember, when we have an if and only if type theorem, we actually have to prove two things. First, I'm going to assume that this is true and show that this is true. All right. Well, our definition says if this limit exists, then for every delta such that f of x minus L is less than epsilon, sorry, I should have said epsilon there, there exists a delta such that the absolute value of f of x minus L is less than epsilon when the absolute value of x minus c is less than delta. Okay, remember what I showed on the previous slide, right? This is the same as saying negative delta less than x minus c less than positive delta, and then you can add c to both sides. C minus delta is less than x is less than c plus delta. Okay, but that's what I need, right? If every x in that interval maps into this interval on the y-axis, then surely every x in this smaller interval does, and that means the right-hand limit also equals L. And again, if this big interval maps into the epsilon interval, then this smaller interval also does, and that proves the left-hand limit, right? And that's all there is to it. That does that side. Now, remember again, because this is an if and only if limit, we have to show both ways. Now, I'm going to assume that this is true and show that this is. Okay, well, you can use a very similar argument. Over here, there exists a delta such that when C is less than X is less than C plus, let's call it delta R, because that's the right-hand limit, then the absolute value of f of x minus L is less than epsilon. And with the left-hand limit, there exists a delta such that when A is, nope, this is the left-hand limit, I got to go the other way. C minus delta, let's call this delta L, is less than X is less than C. Then again, the absolute value of f of x minus L is less than epsilon. We'll do this. Let delta equal the minimum of delta R and delta L, right? In this case, that means that both sides are covered, right? This means that when the absolute value of x minus C is less than delta, my minimum, then the absolute value of f of x minus L is less than epsilon. And that's what I needed to show. Right, there's the other half. So this left and right hand limit theorem, this isn't just a theoretical consideration. We can actually use this to do stuff. Right, and I want to show, I'm going to use it to show that this limit is equal to 1. And to do that, just in case you need to go back and refresh real quick, I'm going to use the squeeze theorem here in a minute to get to this conclusion. So, just at first glance, you might be tempted, we already talked about trig functions a lot, but you might be tempted to do what we've done with every other limit we've seen, with the polynomials and such, and just kind of put 0 in and see what happens. Right, well, if you do, you get sine of 0 over 0, and the sine of 0 is 0, so okay, that's 0 divided by 0, and you can't divide anything by 0, including 0 itself, so that's undefined. Just like you learned all the way back in, in your basic algebra classes. And hopefully at this point, you're starting to see, I'm not disputing what you learned in algebra, that 0 over 0 is absolutely undefined, but hopefully, based on all the examples we've seen so far, you're kind of starting to see that the situation is maybe a little more subtle than that, right? Well, it may be undefined at that exact value of 0. It's still doing interesting things in a neighborhood of 0. All right, so let's see how we can show this. All right, to do this, I'm going to need a diagram, and I'm going to warn you up front before I click on this, go to this to put it in here, to put it on the slide. It's a little messy. Okay, there's a lot going on in here, but it's really not that bad. Now, the first thing I did is I drew this circle, right? And the radius of the circle is 1. It's a unit circle. It's a trigonometry thing, right? Makes sense. We're going to go to a unit circle. And I've got the angle theta down here. So far, this is trigonometry 101. Now, I've added all this other stuff, and let's take a look. I want to look at some specific pieces here. First, look at triangle OAP. That's this triangle here inside the circle. So I want to look at the area of triangle OAP. Right, so next I want to step just a little bit further out and take a look at sector OAP. Well, the sector is really the same thing, only it includes that little segment of the circle out there. Okay, well, the area of triangle OAP is going to be less than the area of sector OAP, because the sector also has that little segment outside. Okay, now we got to go one step further and look at triangle OAT. That's this big guy here. All right, that is still bigger than area triangle AOT. That's bigger than both of the other two objects. Okay, so we've got this inequality, and that's great. So what I want to do now, I'm going to clean up a little here. What I want to do now is rewrite these areas in terms of the radius and the angle. Right? We should be able to do that. So let's see. The area of triangle OAP, okay, that's 1/2 the base times the height. Well, the base is, let me write, I don't want to skip too much. This is 1/2 base times height. Well, the base is this, right? But that's a radius of the circle. So the base is just 1. So this is 1/2 times 1. And the height, that's this line here. But remember, right? Just temporarily, let's call this x, right? The sine of theta is x over 1, but that's just x, right? So the height of my triangle is sine theta. All right, so my total area is 1/2 sine theta. And if you think, you may have actually seen a formula back in your trigonometry class for the area of a triangle that was really similar to this. Okay, so that is the area of, what am I talking? That's the area of my triangle. Okay, so now let's talk about the area of the sector. Okay, well, the area of the sector is, I'm pulling out a geometry formula here, it's 1/2 r squared theta. But r, that's just 1. So this is 1/2 theta. And then finally, my triangle AOT. Well, this is also a right triangle, right? So the area is 1/2 the base times the height, right? Well, what do I have here? The base here is the same as the base of my other triangle. So this is 1/2. The base is 1. And let's see, to get the height, well, let's call this, I don't want to use x again, so let's call this y, right? Then I know, I'm using my trig definitions again. The tangent of theta is y divided by 1. That's opposite over adjacent, which is just y. So this is times the tangent of theta. All right, so this is less than 1/2 tangent theta. Okay, excellent. Well, now let's see, where am I going to go next? I'm going to rewrite this. I'm going to make this sine theta over 2. No, excuse me. Let's multiply both sides by 2. You know, everybody has a 1/2, right? So let's multiply everything by 2, and this becomes sine theta is less than theta is less than, I'm going to make one change here. Tangent of theta is sine theta over cosine theta, right? Okay, now my next step, and here comes the left versus right hand limit parts. Okay, I'm going to divide both sides, or all three parts, by sine theta. Now, you probably remember back in your trig and even your algebra classes, dividing by something with a variable in it is a sketchy thing to do with an inequality, because you don't know if it's positive or negative. You don't know if you should switch the direction of the inequality or not. Well, for this part of the proof, I'm going to focus on the right-hand limit. Right? In other words, I'm only looking at values of theta to the right of 0, and because we're taking a limit, we're looking at small values, also less than pi over 2. Well, that's the first quadrant, right? And in the first quadrant, the sign is always positive. So it's okay in this limited case for me to divide everything by the sine of theta, because I know that on the right-hand side of 0, the sine of theta is positive. All right, so what happens? Stuff cancels here. 1 is less than theta is less than the sine of theta is less than 1 over the cosine of theta. Okay, excellent. Well, let's flip both sides over, right? I can do that. I'm going to flip all three parts over. Remember what happens when we do that with an inequality. The direction of the inequality changes. So this becomes 1 over 1 is greater than sine theta over theta is, whoops, I didn't switch my inequality, is greater than cosine theta over 1. In other words, cosine theta is less than sine theta over theta is less than 1. Excellent. Now, this is what I need, right? I'm going to take the limit of both sides of this. And I'm going to specifically only going to take the right-hand limit, right? The limit as theta approaches 0 from the right of cosine theta is 1. We saw that. If you didn't see that, it's in one of the exercises on the website, right? On the website, on the online class that goes with the lectures. And the limit theta approaches 0 from the right of 1 is also 1. Okay, so what have I shown? So because sine theta over theta is sandwiched between these two functions, which are both going to the same, they're both narrowing down to the same number at that point. That means that the limit of sine theta, limit sine theta over theta, theta approaches 0 from the right, is equal to 1. Okay, awesome. Well, look, how about the left-hand side? All right, well, for the left-hand side, remember, sine of theta and theta are both odd functions, right? And when you divide an odd function by an odd function, you get an even function, right? And even functions are symmetric about the y-axis, right? And this symmetry implies that the left-hand limit has the same value as the right-hand limit. In other words, the limit theta approaches 0 from the left, sine theta over theta, is also 1. Now we can use our theorem. Because the left-hand limit and the right-hand limits are the same, the two-sided limit also has to equal that number. Okay, so this is going to open a door now. All right, this is going to open a door. We can do all sorts of new stuff. Take a look at this thing. Okay, there's a little bit of a problem here. Okay, little bit of a problem. our theorem doesn't have anything to say about the sine of 2 theta, right? Our theorem just talks about theta. Okay, well, there's a little typo here. This should be theta, not x. Okay, here's what I'm going to do, right? I'm going to make a little substitution, right? I'm going to let x equal 2 theta. All right, so if I do that, then this becomes the limit of the sine of x over, and let's say I want to get rid of that theta 2. Well, if x equals 2 theta, then theta equals x over 2. So let's make that replacement, x over 2. And now I also want my limit to be in terms of x. I want this to be x approaches something. Well, look at my definition here, right? As x, the limit as theta approaches 0 of 2 theta is the same as the limit as theta approaches 0 of theta. And I'm going to use my limit properties. I'm going to bring that 2 out front. This is just 2 times 0, which is 0. But look, the limit of 2 theta, that's the same as the limit of x, right? So the limit as x approaches 0 is also going to be 0. Now I can clean this up. This is the limit x approaches 0, 2 sine x over x. Now again, use our limit properties, bring that 2 out in front. This is 2 limit x approaches 0 sine x over x. That one I know. That's what we're looking at on the last slide. That's just 1. So this is 2 times 1, which is 2. So you see, it takes a little manipulation sometimes, right? But I can do a whole other category of limits now. Okay, so let's look at one more here. And remember, when you're looking at these, sometimes people see these and they, wow, that's a big complicated mess. But look, apply the properties, right? Apply the limit properties. First, let's split that fraction up. This is the limit. You see, I keep mixing up my variables. That should be theta. The limit as theta approaches 0 of theta over 3 theta plus sine theta over 3 theta. And this bit simplifies, right? That's just 1/3. Now, let's split it up. We have a limit property that says I can split up a sum. This is the limit theta approaches 0 of 1/3 plus the limit theta approaches 0 sine theta over 3 theta. Limit of this first limit, that's just 1/3. The limit of a constant is just the constant. I don't care what the variable is. Over here, I'm going to bring this 3 out. I'm going to make this plus 1/3. The limit theta approaches 0 sine theta over theta. And that's just 1. So this is 1/3 plus 1/3, which is 2/3. Okay, so that's left and right hand limits. Okay, so where are we going to go now? Well, there's another kind of edge case, if you will, that we still haven't talked about. How about limits involving infinity? For example, as x gets really big, what does the function do? Well, it turns out I can talk about limits at infinity. I can ask, for example, what is the limit of 1 over x as x approaches infinity? You see, this is another example where I'm really okay. I'm really glad that our limit definition doesn't require the function to be defined at a certain point. No function is defined at infinity. Infinity isn't a number. Functions, it certainly isn't a real number. Functions can't be defined there. But we can still talk about it, right? Because our limit definition doesn't require functions to actually be defined at the point, if you will, that we're talking about, right? So that's where we're going to go in the next lecture.